Thanks to you, Stefania. Thanks to everyone attending. I will switch off my camera because I'm getting very little bandwidth ESA. I don't know why. And Richard has kindly agreed to advance the slides for me. But thanks, Stefania, for the invitation once again. And for your introduction. I am now with the Earth Mission Science Division, where I work developing the new missions for ESA, and some of them are really quite exciting, like Crystal, Copernicus expansion mission to look at the polar regions. In today's presentation, I'll be dealing a little bit with what I've been doing in the past, in the last 3 or 4 years, working with the ESA Climate Office after, like you said, Stefania, a long spell with the National Oceanography Center in Southampton. So, but what you see today is material that has been collated and provided by my colleagues in the Climate Office and colleagues working in the ESA Climate Change Initiative. Next slide, please. So the Climate Office is in Harwell in Green, Oxfordshire. It's the focal point in ESA for everything related to climate and climate change. You see here. Next slide. And the purpose of the Earth observation for climate is really to take the pulse of our planet. So look at the host of different variables. You can click on the globe, perhaps Richard, and it will animate. And so it's one Earth, but there's a number of different variables that we can measure from space, like the vital parameters of a patient. And that's really what we do in Earth observation. And today I'm going to show you some results on these. Next slide. What I'm going to say programmatically is within a big program of ESA, of the European Space Agency, called the Climate Change Initiative, which aims at generating long time series of all the different essential climate variables. Next slide. The next slide has got the objective spelled out, realize the full potential of all the archives that we got, long-term and global, because we've got data over the last 40 years. And it is meant as a contribution to the ECV databases that the United Nations Framework Convention for Climate Change is requiring. So our data normally then will feed into the various assessment reports that the UNFCCC and the IPCC churn out. So what are these essential climate variables? So we see them in the next slide, please, Richard. You see they cover all the different domains. You've got 21 variables listed there, and those are all variables that we can list. We can see from space. If you click once, it will animate some text. If you click on, yes, there it is. So the World Meteorological Organization has defined 54 of these vital parameters of the Earth, and 36 of them can be seen from space. And at the moment, we are monitoring them and generating a long time data set for 21 of them through actually the same number of contrasts. It's actually, we've got 23 contrasts because we do the ice sheets in Antarctica and in Greenland separately. And for land cover, which is one of the land parameters, of course, we do a global land cover map, but also a high resolution land cover of special areas. So if you go to the next slide, we see all these essential climate variables rearranged into domains: oceanic, terrestrial, which also has the cryosphere, and atmospheric. And this slide also has some of the variables that are related to what Pepin was saying a moment ago. So we've got greenhouse gases and the ozone, of course, that we can observe. But there's also a number of cross ECV projects, like one on sea level budget closure that you see on the bottom of the slide, and some a project across the terrestrial and atmospheric on the carbon cycle. On top of that, we've got fellowships and education resources and so on, and a project devoted to the interface with the modeling group, the climate modeling user group that you see on the left-hand side of this slide. I will tell you something about that later. Let's go to the next slide, which is just a title, because it opens a section where I'm going to show you now some examples and results of some of the ECVs that we monitor of the cryosphere and the ocean. Let's start from the next slide of Antarctica, of course, and there should be an animation. Yes, so with altimeters, we are able to trace the elevation of the Antarctic ice sheet and then see how it evolves in time. For instance, Cryosat, one of the ESA Earth Explorer, has been absolutely instrumental in monitoring this. And we can derive a rate of change. So you see they are highlighted in West Antarctica, all those regions in the red, where we got a higher rate of change. We can go to the next slide, because the next slide has got the sea level contribution due to this melting ice. And again, Richard, you might have to click to see the animation. With our data, we've been able to separate the contribution to sea level due to melting ice in Antarctica and in Greenland, and the sum of the two. And it's immediately evident in this slide that while it was the contribution of the melting ice sheets was 2 millimeters per decade, not much in the late 1990s, is now over 13 millimeters per decade. So more than 1 millimeter, more than 1.3 millimeters per year, which is, about 1/3 of the overall increase that we are seeing. I apologize. We are in the countryside, and the neighbors is just starting operating a tractor. Sorry about that. So you may hear some background noise. So if we go to the next slide, we look at glaciers and melting glaciers, and here you see the retreat of Columbia Glacier in Alaska from Copernicus, Sentinel-2, and Landsat, and we can compute the loss of ice since the start of the observation, and glaciers have been raising sea level by almost 3 centimeters. If we go to the next slide, in fact, we see a map taken from a paper in Nature from the Glacier CCI project, looking at the glacial ice loss over all the different provinces of glaciers around the world, where you see almost everywhere we've seen a big loss. And like this that we do for glaciers, so we can have a similar look at the sea ice, which is in the next slide. We see over the years, from a combination of altimeters and imaging sensors, a decline of the Arctic sea ice. You see the map, which is from the EUMETSAT OSI-SAF. The OSI-SAF is an operational service for sea ice, but it's fed by research and development, which is done by the ESA CCI Sea Ice project, because the CCI, the Climate Change Initiative, is a research project that develops the algorithms that then are the foundation of the operational services. And I'm sure we'll hear more about sea ice in the next talk by Phil Huang, who's an expert in this domain. But we're still talking about ice. If we go to the next slide, we will see a summary of what we've lost and what we are losing. This ice mass change monitoring. We've been able to partition the loss of ice, which is like a 10-kilometer cube of ice every year. In case you're wondering, that base map over there is a map of New York. That peninsula in the middle is Manhattan. So every year we are losing an ice cube of 10 kilometers of side. And we've seen these over the last 30 years and so we've lost 28 trillion tons of ice, and we are able to partition this loss into all the various contributions. You see those slices representing what we're losing from glaciers, the ice sheets, the ice shelves, the Arctic sea ice and Antarctic sea ice. And of course, the bottom ones then contribute to sea level. The top ones in sea ice do not, to a first approximation, change the sea level, but overall it's a big loss. And of course, the loss of sea ice is then fundamental for the energy budget because it changes the albedo of our planet. So let's go to the next slide. We then observe directly sea level from space, from altimeters. And if you click once, Richard, there's some good bullet points, which sea level rise, we do not just see it rising, but the rate is accelerating. You see on the top left, it was 3.2 millimeters per year. It's now nearing, over the last few years, 5 millimeters per year. And ESA, we are generating long-term observation records and doing all the research and development on the algorithms. Then again, they're taken up by the operational services like CMEMS or C3S. Go to the next slide, Richard, because I want to mention that when we created these long data sets, we have to harmonize observation from a string of different sensors that have been flown in time. That's the timeline of the altimetry missions. And in the sea level CCI, all those observations are harmonized and aligned and they intercalibrated so that you end up with a single global mean sea level curve. And if you click once, I'd like to take this opportunity to highlight that the radar altimetry era started exactly 30 years ago with the modern radar altimetry era on the 17th of July 1991. So it's 30 years and 2 days. We've been celebrating this anniversary on Saturday. Let's go to the next slide. We can look at a budget closure. So with glaciers, ice sheets, sea level, we can try to close the budget of sea level and look at all the different components and sum them up and see whether we match the observed sea level rise, which we do, which is important to gain confidence in our knowledge of all the different processes that contribute to sea level rise. And this is an excellent example of a cross-ECV integration to target directly one of the Earth's cycle, the water cycle. Let's go to the next slide. And we're still remaining in the cryosphere because with a combination of different sensors, so we can look at the permafrost thaw in the north. There's a CCI permafrost project, which is producing very interesting results. I do not have results in this presentation on snow, but I can say, and Richard knows it because you are involved in the CCI snow, that also the observations of snow from space are quite powerful and producing excellent data records. So we go to the next slide. We move a little bit over the open ocean, and we look at ocean color here, which helps us to track the carbon pump in the ocean. We've been deriving, for instance, a biological climate indicator for the ocean, primary production. In that paper that you see referenced there, which highlights which regions of the ocean are more productive and how things change from year to year. In the next slide, then we see our measurements of sea surface temperature. Come in a moment, there it is. The warming ocean, you see in the plot in the bottom left, the global sea surface temperature monthly anomaly. A bit noisy in the 1980s and 90s, but then it becomes clearer and clearer and dominated by the big El Niños in 1997, you see, but with a clear trend showing the global warming in the ocean. And you might see in the top left plot a sort of pulsating climatology, daily climatology built over 40 years of data. We've got 4 trillion satellite measurements with 38 years of data that capture the global annual cycle in the ocean. Let's go to the next slide, because there's still another pair of yes, this is good. It's a very mature data set built on sea surface temperature from infrared sensors, but we are augmenting it now with passive microwave. There's always new research and development to bring in more observations into these climate data records. Let's go to the next slide now, which shows the sea state, which we derive from altimetry. This is a climatology, the mean significant wave height in the 2010s from the sea state CCI version 1 dataset. And in the next slide, an experimental product, which is the change in the 2010s with respect to the 1990s, showing that, for instance, when you compare those 2 decades, parts of the Southern Ocean have got more stormy in terms of sea state. And the last ECV that I want to cover in the next slide is the sea surface salinity, very important for modeling, essential for ocean modeling. You can perhaps animate the map, Richard, if you click on it, and will show the time series. And this is a unique data set built in collaboration with NASA, which merges 3 different missions, ESMOS, Aquarius, and the SMAP, and gives a global view of salinity in the global ocean that we simply didn't have before. It's essential for modeling ocean circulation and the water cycle. So let's follow on. We've seen some examples. I'll wrap up by saying some key facts on the CCI. Let's go to the next slide. These ECV datasets that we get from the CCI are research quality. They are born of climate science requirements in a cycle that goes through the development of the algorithms, the data processing, generating the products, and then we get the feedback from the users. The data are archived and disseminated, they're used, and the users gives feedback to update the requirements. And we go around in a cycle like that, and then when things are mature enough, they can be operationalized by the climate services. If you click once, there's a number of features of the CCI data, and I just want to highlight one, the one that I put in blue, that all these data have uncertainty, their uncertainty fully characterized. Normally it's an uncertainty per pixel, which is essential for modelers wanting to use these data. If you go to the next slide, I want to highlight this climate modeling user group, which is a specific project in the CCI constellation, the CCI portfolio, where we interact with the climate modeling community, and we make sure that they take up the CCI data, the ECVS, the climate data records, for their modeling simulations. And so it's like a big forum where we periodically meet, and it's a project led by the Met Office with the main modelers in Europe. Let's go to the next slide then. And you hit twice, it will bring the two next bullet points, because this is just what we know. Okay. This is just how we contribute to the IPCC assessment cycle, producing papers based on the data that then feed into the assessment reports. And we had a big contribution, for instance, to the special report on the oceans and cryosphere and a changing climate, with 38 papers based on the CCI, and some of our CCI scientists authors in the special report. And also in the AR 6, there's 9 chapters with CCI authors at the moment. Let's go to the next slide, which very quickly just shows that then the research uptake goes into all these state of the climate reports from various institutions, including Copernicus, ECMWF, and so on, that take up CCI data. And over 950 peer-reviewed papers based on the CCI data. Go to the next. We are getting to the end of my presentation. You might ask now, where do I get to the data? Where do I get to know more? The website is simple, climate.esa.int. It's the hub for climate in ESA, so it's a very simple address. And there you also find, there's a link from the website, a nice application to showcase the data sets, very interactive, you see there. But if you go to the next slide, Richard, it shows also a direct dashboard available on the site, climate.esa.int/data. And if you click once, Richard, it brings up again the features of these data sets available for download through there. And I've highlighted, of course, the top one, which is free and open to all. So that's the way you can get to this climate quality, fully uncertainty characterized global long time series of data over more than 20 essential climate variables, the vital parameters of our planet. You can go to the next slide, Richard, and I thank you very much for your attention. I'm ready to take any questions. Thank you.